I'm Fergus Noble.
And I'm Colin Beighley.
We're from Swift Navigation. So this is going to be a talk in three parts. First of all, we're going to try and give you some motivation as to why GPS would be an interesting topic for hackers. Then the bulk of the talk is really going to be a technical discussion about how GPS works, because we think this is really interesting and not many people know all the details. There's a lot of good stuff there. So we're going to focus on that. And then at the end, we're going to present a couple of new tools that we've been working on, which should provide a nice platform for hackers to experiment with this stuff. There's a link up there. Actually, that notes PDF is not yet available. We'll try and get it up there shortly after the talk. And if we'll be in the Q&A room, room 3. It's just right out of the door and then right again after the talk for about an hour or so. Okay.
Okay. Wow, there's a lot of people here. We were kind of worried about after the celebrations last night that there wouldn't be anyone here, but I guess we have the opposite problem. So why is GPS interesting for hackers? Why are we doing a DEF CON presentation about it? Well, GPS devices are ubiquitous. There are estimated to be like in the high hundreds of millions of them in various devices around the world. So they're very common and very widely used, but there are very few open source projects that implement a high-performance embedded GPS receiver. None, in fact, other than ours that we know of. And so we think that it is a project that we very interested in you guys. There are a lot of different use cases for GPS receiver that are not. It's hard to design a proprietary receiver that meets all these different use cases optimally, and so we feel that having an open platform allows people to optimize the receiver for their own particular application, which is very useful. There's a lot of different hacker projects that use it. There's been a lot of open source UAV stuff that has become very popular in recent years. There's a lot of open source inertial sensing stuff for these platforms, and we feel that an open source GPS platform would go quite well with these. And then there's the black hat, white hat dynamic, where there is like all of our infrastructure depends highly on GPS and on the unencrypted signals, which there's massive vulnerabilities there. Financial systems all depend on it, communication systems, transportation systems, you name it. And so there's a lot of interesting problems there with jamming and spoofing these infrastructure that are quite interesting.
Okay, so I thought I'd kind of explain how we ended up here and how this project got started. Colin and I met at a company called Joby Energy. We used to work on making, it was kind of a crazy project. So we were working on building high altitude wind turbines, which is where you take a rigid winged kite, put some big propellers on it, tether it to the ground and fly it up like a kite into the jet stream and hope to generate power. So the photo you've got here is one of our prototypes. It's just like a little, I think it was a couple meters span, conventional UAV, basically only with a tether holding it to the ground. And you would fly this thing up, and it would autonomously fly circles into the wind. And this thing was pulling like 8 Gs continuously, I don't know the airspeed, like 100 miles an hour, 20 feet off the ground. And we were looking for GPS systems which could, offer that kind of performance. And we really just couldn't find anything that was suitable. And we also couldn't find any open source platforms which we could use to adapt to our needs either. So we decided to start our own project. And we worked on it with Joby Energy for a couple of years, and a couple of months ago decided to spin off and start working on it full time. So I guess that's why we got here. You know, we really found this need to have a flexible, customizable platform which you could use in these you know, high dynamic environments, other more demanding applications than could be met by just the type of GPS you have in your cell phone.
So here's another UAV platform that we think will benefit greatly from this project. I want to insert a plug for our friends at Transition Robotics. They're giving a talk tomorrow about Paparazzi, the open source autopilot. And that's at 3 tomorrow?
It's on Sunday at 4.
Or Sunday, sorry. Yeah, Sunday at 4. Yeah, so like centimeter level position hold for things like this, autonomous landing. Yeah, there's many different applications. And another huge area of application is research. Spoofing and jamming, you guys may have heard about Todd Humphrey and University of Texas at Austin, their recent demonstration of bringing a drone out of the sky with spoofing. There are many there are many cases of just very simple, like jamming devices. Yeah, so like there's been cases of oh man.
So, yeah, there's been a couple of cases recently where truckers have been the trucking companies have been installing GPSs in all of their vehicles so that their drivers don't drive too many hours, so they take all the breaks they're supposed to take. And of course, people have made these very simple, just like white noise source jammers, which block the GPS signal so they can, you know, drive longer or whatever. And there's been a couple of cases recently where people, you know, these trucks have pulled up outside airports, and I think I can't remember the airfield in question, but it like shut down a major international airport for a day until someone found it. And this is just a really simple device. So there's a lot of work. It's a very open area. How can we combat jamming or spoofing and detect it? Or also, you know, what techniques could we implement to, you know, to do more sophisticated jamming or spoofing, more on the, you know, kind of attacking side of things. But yeah, do you want to take over for the rest of it?
There's been a lot of research into what's called multipath, which you tend to get in places like urban canyons. In a metropolitan area with like very large buildings, you don't know exactly where the signal is coming from. It could be coming from the satellite or bouncing off something. There are other what are called GNSS, global navigation satellite systems other than GPS. The Russians built one called GLONASS, which is also fully operational, but not quite as cool. Some kind of weird engineering decisions there. But Galileo, which is the new European system that is being brung up. Compass is a regional, Compass is a system developed by China. And then there's a whole host of advanced positioning techniques that there's a lot of research into. You have carrier phase RTK, which can give you down to a few centimeters resolution. Survey grade post-processing, which can give you into the millimeter range. And there's a lot of research with fusing inertial sensors into positioning systems with GPS.
Okay, so I guess we'll move on to the kind of the meat of the presentation. Hopefully that's given you a bit of a justification as to why this might be an interesting area to look at. So we're going to give you a run through of how GPS works, just in basic terms. So let's get started. So the first thing we're going to look at is how you might find the position of the receiver. Basically, this works through measuring distances from satellites. So if you imagine you have your GPS satellite somewhere in space here, if you imagine you had some magic ruler through space where you could just measure the distance, not the vector, just the distance from the satellite to your receiver, if you had just one satellite, then knowing that one distance puts your receiver anywhere on the surface of a sphere of a constant distance away from the satellite. If you imagine you had two satellites now and you had a distance for each of them, then where those two spheres intersect, you're left with just a circle. So now we know, given the distances from two satellites, that our receiver must be somewhere on a circle. And you see how this is going to go. If we add 3, then we're going to be left with just two points where these spheres intersect. You could imagine if you took any two pairs of those spheres, they're going to make a circle, and then the two circles are going to intersect at only only 2 points. And usually in practice, this would be enough to determine the position of the receiver, because one of those points is almost always like miles off in space and can be completely discarded. So given some assumptions about where a sane position for the receiver to be is, that pretty much locks it down to just one position. So if we can measure these distances, then that's how we're going to go about finding our position. Note also you need to know the positions of the satellites in space in order to give some coordinates to that point. However, there's one slight complication. We don't have any way, any magic space ruler to measure these distances. All we can do is, or the best we can do, is measure a time of flight of a signal sent from the satellite to the receiver. And this time, with the speed of light, gives you a distance. The trouble is, the clock on the receiver is not synchronized to the clocks on the satellites. All the satellites have a synchronized clock, so they all transmit the signal at the same time, but you don't know exactly when they did it, because you may have some error in your clock. So that corresponds to an amount of time, an unknown amount of time added in common to all of these times of flight, which is unknown. And the way we get around that is actually by adding a fourth satellite, and that just locks down that extra degree of freedom, gives you the extra information you need to uniquely determine that unknown time period. So it's just 4 equations, 4 unknowns, which is why if you've got a GPS receiver in your car or something, it will only start giving you a position solution when it's got 4 satellites.
So now we know it's all about distances to the satellites. So how can we measure these distances? So we can't measure the distances directly with our magic ruler, so we measure flight times instead. So you can see at the top here, we have a diagram, the distance between the satellite's antenna and the antenna on Earth. At the bottom, we have an impulse traveling from our satellite. It starts at time equals 0, and it arrives at our antenna on Earth at time equals distance divided by the speed of light. So given that we know the speed at which these waves travel, all we need to know is the time to figure out the distance. So how can we measure that time? We can measure the time by measuring the phase of certain codes that the satellites transmit. So in this diagram, you can see 2 satellites, and they each transmit a unique code. These codes are, for the signals that we're discussing, are 123 bits long. That's 123, not 124, or 1023, not 1024, excuse me. And they're transmitted at a rate of 1.023 megahertz, which gives them a period of 1 millisecond. So what we do is we measure the relative flight time of these signals. So you can see that the start of each signal is transmitted at the same time from each satellite. You can see bit N, they've both just transmitted. But for satellite 1, we've just received, or we're just about to receive bit 0. For satellite 2, we're just about to receive bit 42, which illustrates that we receive the start of each of those periods at different times. So we measure the relative phase between those, which gives us the relative distance to each of the satellites. Note there's still a common offset that we don't know, which when we solve for the time, that fourth variable, then we're able to eliminate that.
Okay, so let's talk a bit about the low-level details of how these signals are actually transmitted, how they're modulated, and what's sent from the satellite. So, as Colin said, the main thing which is transmitted is what we call the code. It's a 1023-bit bit sequence, which we'll talk about in a lot more detail. How that's actually derived. It's transmitted at a bit over a megahertz, so it's got a period of 1 millisecond per code. But this code is fixed. It's the same code just repeating over and over again for a given satellite. Each satellite may have, or does have, a different code, but for a given satellite, that code is fixed. And now, whilst it's going to allow us to derive some timing information, we can't use that to transmit any data because we can't change anything. So piggybacking on top of that code, we're going to add a low-speed data channel, what's called a navigation message, or navigation data. And that's a 50 baud data message, and that's modulated just by flipping all of the bits in the code. So I said the code's got a period of 1 millisecond, so 50 baud, so it's 20 milliseconds. Every 20 repetitions of the code, we're just going to flip all of the bits in that code, depending on whether we want to send a 1 or a 0 in our navigation data message. So taking those two things together, the code and the navigation message, that's going to give us our bit stream that we want to send, and then that's just modulated using a pretty common technique called binary phase shift keying. Also note the time scales here are really not to scale because the carrier is at just over 1.5 gigahertz. But what we're going to do is we're just going to flip the sign of the carrier depending on whether we want to transmit a 1 or a 0. Because it's a binary phase shift keying system, we've only got two phases, 0 or 180 degree phase shift. So that's just the same as flipping the sign on the carrier. So I guess that's, it's a very common modulation scheme. Okay. So the next thing is that might be of some interest is how we get this radio signal into the digital domain so we can do some processing on it. I'll just go through this really quickly because don't want to go into too much detail, but we have some antenna. The GPS signals are really, really weak, so first thing we're going to do is amplify them with a pretty high gain, very low noise amplifier. There's like a bunch of other things in that piece of spectrum, a few other satellite navigation systems are there, and different other things that we're not interested in. So the next thing we're going to do is just filter all of that stuff out, just have a nice narrow bandpass filter which is going to select just our GPS signals. It's about 2 megahertz of bandwidth that we're interested in. This is a very common radio architecture. Almost every radio works in the same way. So now we've got our 2 megahertz bit of GPS spectrum that we're interested at, still up around 1.5 gigahertz. And that's obviously way too fast to be easily sampled by an analog to digital converter. So what we're going to do is just shift that 2 megahertz chunk of spectrum down from, say, whatever it is, 1.5 to 1.5 gigahertz plus 2 megahertz down to just 0 to 2 megahertz. This works basically, if you remember your trig identities, if you multiply two sinusoids, you get a sum of frequencies and a difference frequency. So if we take this thing called a mixer, which is just a multiplier, basically an analog multiplier, and we generate our own local sinusoid of a frequency close but not exactly the same as our carrier, then what we're going to do is end up with a difference of those frequencies. So say we set this to this local oscillator to 2 megahertz different from our carrier, then the difference in those frequencies is going to be 2 megahertz, and we're going to end up with that same signal shifted down 0 to 2 megahertz. And we're also going to have another component, which is the sum of frequencies, which is going to be way off at like 3 gigahertz or something. So the next stage is to just filter that out, and we're left with our signal shifted down where we can just sample it directly with an ADC. Okay. So now let's talk about how we can measure this code phase that we talked about. So just introduce a couple of, mathematical bit of background. I'm sure a lot of you will be familiar with this, but it doesn't hurt to go through it again. The basic way we're going to measure the code phase, just going back, so the code phase is this idea of which bit you're on in your sequence in your code. You want to determine what position you're currently receiving at, so that you can compare the signals from the different satellites. So the way we do this is all centered around correlations. So to just go back over what a correlation is, what we're going to do is imagine we have two different bit sequences. What we're going to do is take them bit by bit and just compare the two bits. So you could say multiply the two bits, and if they're the same, then we're going to put a +1. And if they're, like in this lower diagram, if they're different, then we're going to put a -1. And we're going to go through the whole sequence and just compare the bits bit by bit, and then add up all these +1s and -1s that we've collected at the bottom to give us our correlation. That's just a numeric answer. And this is a kind of metric of how similar two signals are. If it's a higher number, then they're closer to each other in some sense. So for example, if you had two signals that were the same, and you performed this operation and shifted one of the signals relative to the other, well, imagine first of all that you didn't shift it at all, then of course all the bits are going to be the same. So our every bit down here is going to be a +1, and the sum is just going to be the length of the bit sequence. This would be a perfect correlation. Now imagine we had the same signal, but now we shifted it one bit to the right down here. A lot of the bits are now not going to line up, and if we had some longer sequences with where there were several high bits in a row, for example, you might get some bits still correlating, but on the whole, it's going to be massively reduced magnitude of the correlation. So that's a correlation where you just take these two bit sequences, compare them, and come up with this sum which tells you how similar they are. A simple extension to that is a cross correlation, where we're going to take two signals and perform a correlation multiple times with different shifts, like we've got these two here with a shift of 0 and 1. If you imagine you plotted on a graph all the different possible shifts you could have shifted by, and what the correlation ended up as for those shifts, then you can build up a plot of the cross correlation. So at 0, obviously, you're always going to have a peak, but then for many signals, you might find that it would tail off pretty quickly after you move away from 0. So now let's talk about the codes that the GPS satellites transmit. These were invented by a man named Gold, so they're called Gold codes. It's a special optimal set of codes which have some certain nice properties which we're going to use to allow, which are going to directly allow us to implement this code phase measurement using correlations. They're all you can generate a set of Gold codes for any length 2 to the n minus 1, and there are going to be 2 to the n minus 1 different codes in that set of the same length. And they have basically two nice properties, and they can be shown to be the optimal bit sequences having these properties. So if you take a Gold code and perform the cross correlation with itself, what you find is that obviously at 0 it's going to have a peak, but the Gold codes have this optimal property of having very low correlation elsewhere other than at a shift of 0. So you can say that autocorrelation is as good as you can get an approximation to a delta function for a finite length code. And we'll see how that's going to be useful in a second. The other property is, I said, there are many Gold codes. If you have a certain length, there are many Gold codes in that set. If you take two different ones and perform the cross correlation between two different Gold codes in the same set, you'll find that their cross correlation is 0 everywhere, or as close as you can get to 0 everywhere for a finite length code. And these two properties together are going to be very useful for implementing code phase measurement. So how do we put this into practice? If we imagine we're performing this correlation operation again, and the two bit sequences we're going to use are what we get from our analog front end, the received signal, and what we're going to do is generate a local copy in software of the code that we know the satellite is transmitting. Each satellite is transmitting a different one of these Gold codes out of the same set. So say we knew we were looking for satellite number 10, then we would locally generate the Gold code corresponding to that satellite. And what we're going to do is just try a number of different shifts, or rather find the cross correlation between the incoming signal that we're receiving and this locally generated copy of the code, just by shifting this locally generated code forwards and backwards as the receiver is running, and hopefully, we can generate this cross correlation plot, and we should see a peak. If we remember, the Gold codes had this delta function-like autocorrelation property. When our locally generated code has a shift of 0 relative to the received code, we're going to get a massive peak in our correlation. So if we're trying to find the phase of the received code, it's enough to just shift our locally generated code backwards and forwards until we find this correlation peak, and then we know that our locally generated code must be in perfect phase alignment with the received code. And of course, because we generated our locally generated code, we know its phase, so that allows us to measure the code phase. The second property of these Gold codes is going to allow us to receive from multiple satellites, which is pretty useful, seeing as you need at least 4 satellites to get a solution. All of the GPS satellites transmit on the same frequency, and they're transmitting data modulated in pretty much the same way. So you'd think, how are you going to distinguish between different satellites? If we think back to this property of the Gold codes, that two different Gold codes have 0 cross correlation, then we're going to see that actually if we performed this cross-correlation between, say, satellite A, code from satellite A, and we locally generate satellite A's gold code, then it's going to have this delta function like cross-correlation allowing us to pick out this peak. But if instead we were locally generating a code for satellite B, then it's going to be 0 everywhere, so it's going to make no contribution to the correlation that we measure. So basically, this property of gold codes allows us to have the satellites independent from one another, even though we're receiving them on the same frequency. Okay, so just to sum up why gold codes are cool, they pretty much are the key idea in GPS. There's really three things. They allow us to get this phase information, which allows us to measure the time of flight. This is really the main measurement we want to make. As I just said, they allow us to transmit on the same frequency for all of the satellites and distinguish between them. This is basically a form of CDMA, same technique that's used in modern mobile phone networks. And the third thing is, which I haven't really mentioned, is it allows us to pick up this really, really weak signal. The GPS signal is actually below the thermal noise floor of the receiver, so just the heat in all of the components in your receiver, like knocking carriers around in the silicon, is going to contribute more noise than the actual signal from the GPS satellites itself. So we need some way to be sensitive to such a small signal, and really it comes back to the fact that when we're performing a correlation, we're effectively integrating over a long period. So any noise is going to average to 0, but any contribution from the code is going to be amplified. And so in the case of GPS, we've got 1023-bit codes where we're integrating over 1023 bits or a whole millisecond. So this gives us a huge gain in sensitivity. Okay.
There's another detail that we haven't discussed yet, which is that the satellites are moving so quickly and the frequency that the signals are transmitted on is so high that there is a non-insignificant Doppler shift on the signal when it reaches us of a couple kilohertz. This comes in more important in a second when we talk about acquisition and tracking, but it's just important to know that we talked about down converting the signal from the carrier to a low frequency. You actually, even if that frequency is nominally 0, you typically have to mix it again down in software to accommodate for the Doppler shift. Okay, so the navigation message gives us some information about the orbits of the satellites. So we need the information about where the satellites are to know where our position is in 3 space relative to them. So as we said before, the navigation message is transmitted at 50 baud. There are 20 code periods in each navigation bit. So at the end of the 20 code periods, you may or may not have a flip in the sign of the signal due to the navigation bits. The whole message takes 12.5 minutes to transmit, which is why old school receivers will take 12.5 minutes to give you your first position solution. So to sum up, we have these kind of 2 paths that come together to give us our position solution that come from the code correlations. On the right-hand side is the flow of signal processing to get the ranges to the satellites. You start with the code correlations. From the correlations, you can infer the code phase. From the code phase, you can infer the time of flight. From the time of flight, you can infer the distance to the satellite. On the left-hand side, code correlations also give you the navigation message, which allows you to extract data about satellite positions. And now,
Okay, so in the previous section, we introduced basically so all the operations which we need to implement a GPS receiver. Now we're going to talk a bit more about how these techniques are used in a specific way. And almost all GPS receivers have effectively two modes of operation, which use these same basic operations in two different ways, depending on what you're trying to do. The first of these is called acquisition, and this comes in when your receiver is just starting up from cold, and you have no information about the satellites whatsoever. You don't have any estimate really of what their code phase or the Doppler shift. These are the two parameters that we're interested in that uniquely determine where how we're receiving that satellite is the code phase and Doppler shift. So if you have no information, you start in this mode called acquisition. And we've got these two parameters, and effectively all acquisition is just an exhaustive search over the whole two-dimensional space of code phase and Doppler shift. So here's a plot taken from some real data, and all we've done here is just searched over all the possible values of code phase, 0 to 1023 bits worth of shift, and Doppler shift, I think we're here, the range is plus or minus 5 kilohertz, something like that. And we're just searching, for every point in this space, we try out a cross correlation and plot the magnitude of that of that correlation and see if there's any signal present. And as you can see, you have this noise floor, but then a pretty substantial peak where the satellite is present. But as you can imagine, this is quite a large space, and each of these operations takes a not insignificant amount of time because you're effectively doing a 1023-bit integration. So this is a very expensive process, and we want to avoid doing it if we can. If there's a faster way, we can do it. If we can find a cheaper alternative, then we can provide our user with more frequent updates in the position solution. We can track more satellites at the same time, or we can run at lower power. So we want to avoid using, this is why we can't use acquisition to perform every measurement. And it's also why you would try and make this acquisition grid as coarse as possible. I think that's about all there is to acquisition.
So like Fergus said, acquisition is a very resource-intensive process, and so we use a different method to quote-unquote track the signal once we've acquired it in that two-dimensional space to update that code phase and carrier frequency. So this shows you roughly how the code frequency is updated by the tracking loops. So instead of doing 1023 correlations, or you generally actually do more than that in acquisition, we only have to do 3 correlations. We do one where we think the signal is, and that's the prompt correlation. We do one right before where we think it is, the early correlation, and we do one right after. And through those 3, we can kind of get a metric of how our locally generated code signal matches up with the received code signal. So on the left, you can see the case where it matches up pretty well. The prompt correlation is right in the center of that peak, the correlation peak, and the early and late have approximately the same value. In the center, you can see the early case, where the early correlation is the greatest and the prompt and late are less. And we subtract the late correlation from the early correlation to give us an idea of what our error in our local code is. And you can see when the early minus late correlation is greater than 0, then we know that our code, our locally generated code, is a bit faster than the code that we've received, and so we have to slow it down a little bit on the next integration period. On the right, you can see the late case where the late correlation is the greatest, and you have the opposite case, early minus late correlation is less than 0. So this early minus late correlation is commonly called the discriminator, and that feeds a delay locked loop that helps us filter out our code frequency and get a lock on it. The tracking of the carrier frequency or the Doppler shift is done in a very similar way. The discriminator is calculated slightly differently using the in-phase and quadrature correlations, but it's very similar. Here you can see a plot of some real-time tracking we did. The blue signal is the quadrature signal, and the red signal is the in-phase signal. If you remember from that analog slide, the analog front end, when we sample the signals, we actually have two digital signals that we've sampled, the in-phase and quadrature versions. Those are 90-degree shifted mixed down signals. You can see the nav bit transitions in the red signal as it shifts from like positive 40,000 to negative 40,000. The code and carrier tracking loops are done in such a manner that they ignore these bit transitions. In the beginning, you can see the red signal kind of ramping up, and that corresponds to our tracking loops, the frequency of the code and carrier getting more accurate, and thus the correlation becoming greater.
Okay, so we wanted to focus in this presentation on the technical aspects of GPS because that's what we find interesting, and we wanted to give you a flavor of that side of it. But just briefly, we'll introduce a couple of new tools that you might be interested in using if you were wanted to pursue doing some experimentation in this area. So I guess it's probably good to start with a little survey of what's already available. Very quickly, we have something like a mu-blocks receiver. Really amazing receiver. For like $100, you can get 2.5 meters of accuracy, 5 hertz update in position solution. It's small, it's low power, really nice integrated little unit, more similar to what you have in your car navigation system or your cell phone, but it's completely black box. There's not really anything you can tune on it, no parameters to tweak. You pretty much just get what you're given. And it doesn't implement any of these, Colin mentioned there are these advanced positioning techniques which are pretty useful. For example, carrier phase RTK, where you're taking 2 receivers and doing a differential measurement between the 2 of them, and this gives you like centimeter level precision. And a receiver like this would not implement any higher performance techniques like that. Going up a step, you've got fantastic products from companies like Novotel. I didn't actually get a quote on this receiver, but it's like a 4-figure kind of number. Shaves a meter off the position error compared to a mu-blocks type receiver, and it's got firmware upgrades, so you can add all of these fancy features. But again, it's pretty much just a black box. There are a few basic parameters you can tweak, but it's not very flexible. Going up a step again, in some ways you've got products like the Namaru from some guys at, I think it's the University of New South Wales. So for like $6,600 you can get a really nice platform, and if you buy it you get the source code, you get the board files, you get all of the details of the hardware, so you can go and tweak it, but it's not open source. It's pretty much a closed platform, and it's still fairly bulky and power hungry. It's not something you can just duct tape on your quadcopter and go flying. So we kind of wanted to fill this gap a bit. So I guess the first tool is a library. There are a couple of really good open source GPS toolkit libraries out there, but we found none of them really met our needs. So in libswiftnav, we've tried to implement all of the basic building blocks of a GPS receiver. You know, as Colin talked about, like these tracking loops, performing the navigation solution from the distances, the pseudo ranges, all of these building blocks. Unlike the other libraries that are available, it's designed to be really lightweight. It's portable, standard C, no dependencies, apart from, I think, the C standard library. Even that you could factor out pretty easily. It's fast, it's lean. We run it on a microcontroller, a pretty low power microcontroller. So in contrast to the other existing libraries, which you might run on your machine locally with just an analog to digital converter plugged in, this is something you can run on an embedded system. And it's designed to be flexible. You can prototype new ideas with it quickly. So yeah, hopefully this is something which will prove to be useful to other people. And just briefly, this is a hardware platform which we've come up with. It runs this library that we mentioned. On there you've got a microcontroller. It's the fairly new STM32F4 from ST. It's a Cortex M4 core, so it's pretty lightweight, but it does have a few DSP instructions. It's got hardware single precision floating point, which is pretty handy, and it's pretty low power. We've also got a Spartan 6 on there, FPGA, and that is basically, it doesn't do anything that smart. It's just filled to the brim with very basic correlators, which the STM can go and program to perform correlations against different codes, or all the parameters of the correlation, and just return the result back. It's low power depending on the firmware you're running. It's a little under half a watt. It's small, it's like a couple inches square. So yeah, these are our new tools. And I think we've got a little extra time, so I guess we can take a couple of questions. The cost? So we're currently just gearing up to do a beta run, and we're looking at around $1,000. Yep. No, we haven't. It should build pretty easily on something like a Raspberry Pi. That should work fine. Yeah, you just need to find a way to get your front-end data in, which should be easy enough, but should build on any system with a sane C compiler. Sorry? You'll have to shout. TV tuner chips? We haven't. I know some people have had some success. The GNU Radio guys use those TV tuner chips quite successfully. I'm not sure if they've received GPS. I guess the problem you may have is sensitivity. They're not as sensitive as a dedicated GPS front end. What we've got on the Pixie is a Maxim front end dedicated for GPS. Okay, and we're out of time. So we'll be in Q&A room 3 if anyone else has any questions. Thanks.